We're moving away from pyruvate, or I guess we're carrying that pyruvate now over into what would be starting to be considered aerobic energy metabolism or oxidative phosphorylation. Really, there's two different sites of oxidative phosphorylation. We're going to have citric acid cycle, and we're going to also have the electron transport chain. So these are actually separate entities. They're separate processes, but they're attached in certain ways. They're largely connected by those NADHs and FADHs that we learned are so super important. You'll see that citric acid cycle and Krebs cycle are used pretty interchangeably. Krebs cycle is called Krebs cycle because it was named after the guy that discovered it, which is Hans Krebs. So essentially the primary goal of citric acid cycle or Krebs cycle is just to be removing electrons from acetyl-CoA. So if you remember, when we're walking through glycolysis, we have a 6-carbon molecule of glucose that's been broken down into 2 different 3-carbon molecules. That 3-carbon molecule at the end is called pyruvate, or here they have it labeled as pyruvic acid. And then we actually have to take and convert that pyruvate into acetyl-CoA. What I want you to think of acetyl-CoA as is like the hand stamp to get into the club, right? It's the hand stamp to get into Club Krebs. I promise you, I know how stupid that sounds, but I learned that when I was an undergrad, and I've never forgot it as kind of the entry fee to get into Krebs cycle. I think it's an awesome way to remember it. So how are we going to remove electrons from this 2-carbon acetyl-CoA, and how are we going to use those electrons and hydrogens, really, if you remember, to fuel aerobic energy metabolism, or to kind of get shuttled to the electron transport chain? So there's actually a series of steps that kind of occur in a cyclical fashion, hence the cycle name of it, where we're going to be creating different molecules and actually generating more NADHs and more FADHs. And we'll see that those NADHs and FADHs actually matter more than generating ATP because they have a higher potential energy. For every 1 ATP you produce, you only get 1 ATP's worth of energy. But for every NADH or FADH that you create, you either get 2.5 ATP or you get 1.5 ATP for NADH and FADH respectively. So we're really just trying to pull off electrons here. All we're trying to do, we don't care about tracking carbons anymore. We're tracking electrons at this point. This is going to be what the Krebs cycle really looks like in terms of form. This diagram right here is really just going to be showing you where the carbons are going. So what carbons are you starting with? How are they staying in? And then what carbons are you kind of converting to CO2? I don't really personally care if you understand where the CO2 is coming out right now. We'll talk about it later in respiration sections, but just know that this is kind of where you start generating some CO2, which is why we actually have breathing the way that we do. And that's why we intake oxygen and exhale CO2, is because we're actually producing carbon dioxide during the production of energy, right? Here you can see that acetyl-CoA gets converted into citrate. Citrate gets converted into isocitrate. From isocitrate, we're going to be converted into alpha-ketoglutarate. But if you notice, the important step here is that we're producing an NADH. So this potential energy of 2.5 ATP was just created. As we go from alpha-ketoglutarate to succinyl-CoA, we're creating another 2.5 ATP, essentially, right? Every time you see NADH, you need to be thinking that we're creating ATP with that NADH. And you need to be thinking that that is representing an electron and that is representing a hydrogen ion. From this succinyl-CoA, we're going to create succinate. Sometimes you'll kind of see this occurring at the bottom of figures, and what you're going to be creating from succinyl-CoA and succinate is a GTP. That's guanosine or guanine triphosphate. That is super readily converted into adenosine triphosphate, or ATP. So we actually just count that GTP as 1 ATP. So we've already, in this one, like half of a turn of Krebs cycle, with 1 acetyl-CoA, with 1 pyruvate, we've already created significantly more ATP, or the potential to create significantly more ATP than we ever did with glycolysis. So it's this very large transaction occurring where we're putting in $1 and we're getting out hundreds of dollars. It's kind of like winning the lottery, essentially. After succinate, we're going to convert succinate into fumarate, and we're going to create FADH2. One good way to remember this is that it's the first time that you're seeing the letter F come into the Krebs cycle with fumarate, and that means that you're creating an FADH here. And that FADH, if you remember, is responsible for about 1.5 electrons in the electron transport chain, or 1.5 ATP from the electron transport chain. From fumarate, we're going to create malate. Malate is going to get converted into oxaloacetate, and we're going to get another NADH here. So we have 3 NADHs being created from Krebs cycle, 1 FADH being created from Krebs cycle, and we have an ATP molecule by itself being created from Krebs cycle. So we have the potential energy of a ton of ATP kind of just sitting here readily available, just off of this one turn of Krebs cycle, one time with 1 pyruvate. And how many pyruvate are we creating from glycolysis? 2, right? We're creating 2 pyruvate. So we get 2 acetyl-CoAs. So for every single molecule of glucose to go through glycolysis, we're getting 2 full turns of the electron transport chain. So every number that you see here, double it. This is the exact same figure. We've just added in more information. Everywhere that you see one of these crazy looking lightning bolts is where you're either generating an NADH, an FADH, or additional NADH, if you will. This figure also lists the enzymes that are responsible for the kind of cycling through of Krebs cycle. What I want you to know off of this is simply this first number 3 step. The only enzyme that I really care that you guys know is this first one, or this third enzyme on Krebs cycle, and that's isocitrate dehydrogenase, or IDH. IDH is going to be the rate-limiting enzyme of Krebs cycle, which means that it will control whether or not this reaction, this series of coupled reactions proceeds or gets axed right there and does not continue. So if we run out of some of these intermediates like succinyl-CoA and succinate and fumarate, if we run out of these things, we will actually stop the process right here and no longer proceed with it. So we won't be able to create any more NADH. It will stop. So that's super important to know as we start getting into later stages of exercise metabolism. I also kind of want to highlight up here that you can get in acetyl-CoA from 2 different things. You can bring acetyl-CoA in from either glycolysis via pyruvate, or you can actually bring in acetyl-CoA from the beta oxidation of fatty acids, and that is lipolysis. Beta oxidation means that you're breaking down fats to create acetyl-CoA. If you remember back, fat is just a long string of carbons, and acetyl-CoA is a 2-carbon molecule. So for every one of those long strings of carbon, all we do is cleave off 2 carbon molecules, and we can actually eventually create acetyl-CoA and do it rather rapidly, actually. So while glycolysis, you can only get 2 acetyl-CoA per glucose molecule. Per fat molecule, you can essentially get close to an infinite number of acetyl-CoAs. As many carbons as there are, divided by 2, and that's how many acetyl-CoAs you can generate. So it could be hundreds of turns of Krebs cycle per 1 molecule of fat. So the like reserve tank from fatty acid metabolism is so much greater than glucose. We can burn through our glucose stores for energy a lot faster than we can burn through our fat stores, which is why we have them. Here you can see that we're going to be kind of counting up the potential energy of the aerobic tally. We'll go over in the next video why you get 2.5 ATP in the electron transport chain and why you get 1.5 ATP in the electron transport chain. In the longer video, I kind of talked about this, but you kind of are, it's a goofy table because you're adding across, right? So if you go through glycolysis without moving forward with aerobic metabolism, without carrying those NADHs generated forward, your net output is going to be 2 ATP. Like say that we, for some reason, stop glycolysis immediately. As soon as ATP is generated, then we're going to be done. Only 2 ATP net are going to be generated. However, if we continue on and we actually have some of the electron transport chain running, those NADHs that we generated from Krebs or from glycolysis are actually going to get dropped off into the electron transport chain just as much. So those 2 NADHs that we're going to generate in glycolysis result in 5 ATP at the end of it, which means our total ATP generation from glycolysis is 7. If we then carry over, right, so we go from 2 plus 5 equals 7, we get 2 more NADHs because we're actually converting pyruvate to acetyl-CoA at the very, 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 very top of that figure. We end up 7 plus 5 equals 12. We get 2 GTP, so we get 2 ATP per unit of glucose. So we'll go from down here 12 ATP plus 2 equals 14. You'll get 6 NADH because we get 2 turns out of Krebs cycle per glucose molecule. So we get 15 potential ATP generated. So 14 plus 15 is 29. And then for each one of those 2 FADH that we generate, 1 per molecule of acetyl-CoA, so 2 per molecule of glucose, we get 29 plus 3 ATP because 1.5 times 2 is 3, resulting in 32 ATP. So the next video is going to really be focused on how do we go from these agents of change, these NADHs and these FADHs, to actually creating an energy currency.